Hey guys, it's your host, it's your host Subhra. Welcome to your favorite channel, Subhra the Geek. So guys, today we have another video of our mathematics series, linear algebra series, the fifth video in our series that is on probability. And so these are the series, a few series which I have planned with my very good friend Debayan. He is from industry, he's working for a company as a core data scientist for a couple of years now, and he knows the insight, and he'll cater to you what the industry wants actually from, and what should you learn, and not all the things which are there on the internet. So that's the aim of this series, guys. To stay updated with the series and to get the notification of each and every time we update any content on the channel, do subscribe, do hit the bell notification icon so that you get to stay updated anytime. And guys, if you face any problem during your journey, we have made an exclusive Discord server for you. The link will be in the description box below. So join over there. I and Debayan will be there to help you out in your journey throughout all the series anytime you like. And if you have any suggestions, you can drop it over there also or in the comment section. If you like the video, please give a thumbs up and do share it with your friends and all the people you know so that they also get the benefit of this video. So without further ado, I am your host Shubro, and with me is.
Debayan.
So let's start, shall we? So guys, today we are gonna talk about probability. So let's start at what is probability. So what is probability, you may ask. So to give you in a very simple terms is the amount of times you want something to happen by the total number of times it can happen, or the ratio of amount of times you want it to happen given all the times it can happen is the probability of an event. So at the very beginning, at the onset, we hear about a term called sample space. So what is a sample space? It is nothing but a collection of all the possibilities of a random experiment. If I toss a coin, so what will be all the possibilities? It can come out to be a head, it can come out to be a tail. So if I throw a dice, what will be the possibilities? It can come to be a 1, it can come to be a 2 or 3 or 4 or 5 or 6. So this is the sample space for a dice, and head or tail is a sample space for a coin toss. So that's basically what a sample space is. Nothing more. That's a very simple thing. Like all the possibilities you can happen, or you are performing an event, so all the possibilities you can see is the sample space. So now we can visualize a sample space, and that's what a very famous scientist or mathematician, you can call him, Venn, he invented a diagram for showing this kind of possibilities. Like, okay, so you can visualize this kind of possibilities, and for that he made a very good diagram, very good representation using circles and squares, where the square is the complete or the universal set, and each circle will represent a single class of event which you want to happen. So I'll give a image on the screen, so you can refer to that image over there, and you can understand, like, okay, when two circles intersect, they have a portion which is common to both, and when they do not intersect, like this part is different and this part is different, and we have union. What is union? It's like nothing but the set properties which we have done in our elementary schools. It's completely that. It's the same as Venn diagram, and Venn diagram helps us in probability. So now, based on this kind of diagrams, we have many kinds of probability. So that will be explained by Debayan.
So let's start with an example, right? We're gonna understand the types of probabilities with some example. Let's work with a deck of cards, shall we? Um, a deck of cards that you can find in a local, like recreational shop or somewhere. Those pack of cards have, like, in total they have 52 cards, right? They have a set of Out of those 52 cards, they have a set of black cards, they have a set of red cards, right? And under red cards, there are two classes. One is a diamond set of cards, and another is a heart set of cards. Now, in order to understand a probability, a type of probability called conditional probability, we're going to look at those two specific subclasses of the red set of cards, right? So we know that that there are 52 cards. The number of red cards will be 26, right? So you might say that the probability that of a red card, right, out of the total deck will be 26 by 52, where 26 is the number of red cards and 52 is the total number of cards or the sample space of the card. Out of those 26 cards, you have 13 diamond cards and you have 13 heart cards, right? So you would say that the probability of a heart card, right, or a diamond card will be 13 by 52, where 52 is the total number of cards in the deck and 13 is the total number of heart cards or diamond cards out of the red card subset of the 52 total card pack, right? So conditional probability, this special type of probability, is what we call that. What is the like we ask the question, right? So we ask the question that what is the probability that a card will be heart or diamond given that it's red, right? So let's say what's the probability that a card is diamond given that it's red. This is the notation, or this is the language we use to call about conditional probability, where the probability that the thing that we're asking for is sort of conditioned on, or it's like it's sort of dependent on the next condition that we say. So in our example, we're going to say that the probability of a heart card or a diamond card, it's sort of conditioned on the fact that the card must first be red, otherwise it's not possible, right? So what is the probability that you will have a diamond card or a heart card given that it's a red card? It should be 13 by 26, because now the sample space is the red card set, which is 26 out of 52, and the number of heart cards or diamond cards will be 13 out of those 26. So you'd say that the conditional probability that you will get a diamond card or a heart card given that your sample space is a red card is 13 by 26, or half, or 50%, right? So generically speaking, you will say that the probability of event A, or a scenario A happening or being true, given that some other scenario B or event B has already happened or it's true, that's the conditional probability of A given B. We write it as probability of A given B, and given, the term given is represented by a vertical line like this, right? So you might say probability of A given B. There's also another kind of probability, we sort of is derived from conditional probability. It's sort of represented from there, and it's called the marginal probability. You've heard of the terms marginal in various contexts. If you're reading, like complex financial documents, if you're reading complex news and stuff like that, there will be terms we called marginalized, or marginal probability, or marginal profits, marginal, that we hear the term a lot, right? So what does it mean? What do we have to understand from using the term marginal probability? Can we also be understood using this example that we had for conditional probability? Let's carry on from there. So marginal probability is the probability of a red card given that it has two subtypes called diamond and heart. Let me clarify on that. When we talk about a marginal probability of something, say an event E, right? It implies that event E or scenario E has multiple subtypes, right? In the case of, let's say, we are talking about a red card, right? So the marginal probability of something being a red card A red card can have multiple subtypes. One of them is a diamond red card, it's called the heart red card, right? And we know that their probabilities are 13 by 52, and this one is 13 by 52 as well, right? So you'd say the probability the marginal probability of a red card would be the addition of those two. It should be 26 by 52, right? So if we generalize this to to any other scenario, any other kind of examples, so you'd say that if an event has sub scenarios and each of those sub scenarios have probabilities or subclasses have probabilities, right? So if you say that the marginal probability of some event E happening or being true, that is equal to a summation of all those individual sub scenario probabilities, and that will give you the answer for the marginal probability. So the language that we use in this kind of probability, or for specifically for marginal probability, is we say that we marginalize over the subcategories of the main class to give you the total probability of that main class, right? So in our case, the red deck will have diamond cards and will have heart cards. So we say we marginalized over the diamond and the heart cards to give you the red class probability, which is 26 by 52, which is again half.
So, guys, let's talk about random variables. So, what is a random variable? A random variable is nothing but an outcome of a statistical experiment, you can say. So, if I toss a coin, what will be my outcome? That's a random variable. If I throw a dice, what will be my outcome? That's a random variable. As Debayan mentioned, if I draw a card out of 52, what will be my outcome? That's a random variable. So, random variable based on what and how the things we are choosing can be classified into two terms. One is discrete random variable, one is continuous random variable. And based on this discrete random variables, we have a different set of function, and based on the continuous random variables, we have a different set of functions. So here Debayan will tell you about the function of uh, discrete random variable and continuous random variable.
For these two kinds of random variables, right? So when you hear the term random, right, I want you to understand that these are experimental in that sense that you cannot receive the same number, like there is a probability associated with getting the same number over and over again, right? And the nature of the number can either be discrete, as in they can have fixed values which are not fractional, or they can be fractional but they belong to a finite set, such as if you say discrete, as in like this deck of cards, right? This is a discrete set, taking out a card from a deck of, like taking out a red card or a black card from a deck of cards. This is a discrete random variable, because first of all you do not know what will be the card, so that by definition it's random. You do not know, it's unknowable until you take out the card. But you cannot have half a card, you cannot have a fraction of a card, that's not possible, right? So discrete means individual units are finite, they cannot be broken down into components, and they belong to a finite set. So our set of cards, there are 52 cards, you cannot have one and a half card, you cannot have 2.37 cards, you can't have those fractions. On the other hand, continuous variables or continuous random variables are exactly what they mean. They are continuous, and they have they have decimal points, right? So you can have continuous points between 2 points. Let's say between 2 and 3 you can have 2.1, 2.11, 2.121. You can continue on and on. It's effectively continuous, and you do not have a very specific number over there. It's sort of like messed around, sort of like mixed around between a range of numbers. So when you're trying to calculate the probability of a discrete random variable, is very easy, right? Just like with the example of cards, right? So you find out the number of discrete possibilities, you take out the sample set, which is, with the card example, it's 52. You know there are 52 possibilities of cards, right? It cannot be more, it cannot be less, it cannot be a fraction, it's 52, right? And then you find out those specific cards, red, black, diamond, heart,
Hard.
and you find
Hard.
out specific types. You get the sample set, right? And then you can divide them and get a very good understanding of what is the probability of a certain card being this or that. You can find out conditional probabilities, you can find out marginal probabilities. um, the, the function, or the so-called function that sort of helps you find the probability of a discrete random variable, is called a probability mass function, right? And it tells you, generally speaking, it tells you the probability of a discrete value being in that discrete sample set. Please try to understand, I'm trying to emphasize the word discrete over here, because these are finite. They do not have fractional components to them. They have they have a fixed length, so you cannot break them out into component parts. You cannot break them out into smaller parts. And this function, the probability mass function, tells you the exact probability of a very specific thing happening, and this thing should belong to to that sample set that you are involved in. Or in our case, if you're talking about cards, so the function, the probability mass function, will tell you that the probability of having a red card out of 52 cards will be half 26 by 52. It's a very specific number, and you cannot deviate from that. For continuous random variables, it's a bit different, because you do not have a specific value, you do not have a finite number. It's technically infinite if you consider real number set, right? Real numbers are continuous, and they are technically infinite if you're talking about sets, if you're talking about including them in sets. So if you have a set of values which belong to a real number set, which are continuous, in order to find out the probability of something, you need to have a function called the probability density function. And this is quite different from a probability mass function, because a probability density function does not give you the probability. It's a bit different. um, what the probability density function gives you is the likelihood of a value appearing in that sample space,
Exactly.
right? It's not probability. You cannot say it's that. It's likelihood. That means it's like you cannot define likelihood as probability, because a likelihood sort of condition, it sort of has a conditional probability aspect to it, right? So if you know an information, you can say what's the likelihood of something happening given that information. There's a conditional aspect of it. We're going to talk about this in detail later on when we're talking about machine learning, likelihood functions and stuff like that. But just know this for now: a likelihood is not probability, and a likelihood has a component of conditional probability attached to it, right? So what a probability density function gives you is the likelihood of a value belonging to that continuous set of numbers. And if you perform integration, yes, from calculus integration, right? It gets a little complex very fast. If you perform integration of that function, of this probability density function, between a certain set of numbers, a range of numbers, and those range of numbers must belong to that continuous set, right? Between, let's say, a and b, and where a to b, all of them belong to your continuous variable set, right? If you integrate that, then the value that you will get is actually the probability of a value being between those 2 points for that set. So this is where the probability function comes in, and you can see why it's called the density function, because the density means that the total probability sort of divided up into smaller chunks, and those chunks are technically tends to zero. They are very small, and that's where the calculus part comes in. That's where the integration part comes in, and you have to add them up, all those small discrete sets in that, you can say, you can approximately discrete, to add them up to form a continuous set. And that's why integration comes into the place of probability density functions. You're going to see how important and how versatile these functions are when you're talking about machine learning and feature extraction and feature engineering and those kind of things in our ML series. So there's there's some distributions. There are some concepts called distributions, which are really important in sort of summarizing, probability functions, like we discussed in the previous in the previous section, for continuous as well as for discrete variables. These distributions sort of summarize everything that we can possibly know about those set of numbers, and they sort of help to encapsulate the complexity of those set of numbers into just a very compact form, which you have to just remember a couple of configurations about them, and you can sort of make more predictions, more deductions about them. One of the easiest distributions that we have, that we can talk about, is called a uniform distribution. And in a uniform distribution, um, uh, every probability is the same. The likelihood, or the probability of all the events happening is equated to be the same. That's why it's called uniform distribution. Uniform distribution can be of both, for discrete values as well as for continuous set of values, right? For discrete uniform functions, it's basically just counting things and dividing them up, right? So if you have, like in the case of card examples, if you have 13 diamond cards, you can literally count those cards. There are 13 of them, and you divide by the total number of cards, which is 52, and you get 13 by 52, which is 1 by 4. So it's pretty simple. You just count each of them, and you know that the probability of getting any one of those cards, any one of those diamond cards or heart cards, out of the total deck of 52 is always constant, which is 13 by 52. They don't change, right? In a case of continuous uniform distributions, what you do is you sort of integrate, just like we discussed a couple of moments before, right? So you have a range from A to B. You have a probability density function, because random continuous variables have probability density functions. Please remember that if you just find the value of a density function, you get the likelihood. In order to find the probability of an event happening, you need to integrate between two ranges, A to B, right? So if you perform the integration, you what the answer that you will get is uniform. It's basically just multiplying the same small constant, because it's differential, it's calculus, it's taken as a very small constant which tends to zero. You sum them up between the ranges from A to B, right? And the answer that you get is uniform. It's effectively the same concept. All of them probabilities are same, right? In between, any number between those two ranges will have the same probability, which is a very small number, but it tends to zero, but it's not zero because it's calculus. And if you add them up, you will get a total, get a total number, which is the uniform distribution, a continuous distribution value, probability value of a number that lies between those two ranges, A to B. The next distribution we're going to talk about is something which I believe is one of the most important distributions that you must be very familiar with. Uh, in real life, we use these distributions every day in some form of another, and this comes up way too much when we are actually doing experiments and conducting experiments and actually writing code. So pay attention to this one. This is what we call a Gaussian distribution, and there is another name for it, which is called the normal distribution. It's it's called normal because it is one of the most commonly occurring distribution in natural life and in real world experimentation, that we literally call it the normal distribution. It's so normal. Yeah, so that's the joke over there. um and and the way we work around, or that we configure this distribution, is that it does not work for discrete variables. It only works for continuous variables. So keep that point in mind. The configurations around working with the normal distributions are only two values that you need to remember: the arithmetic mean or average of your set of continuous numbers, and the standard deviation of your continuous numbers. And using these two numbers, you can set up your normal distribution, as shown in the figure beside me. So you have the mean right in front, right in the center, right? And then on the left hand and right hand side, you have the standard deviation. So what you do is that you take steps towards the right and the left in steps of the standard deviation value. So you take one standard deviation to the right or left, you take two standard deviations to the left or the right, and so on. And you will see that the curve sort of flattens out when it almost reaches the three standard deviation or the minus three standard deviation mark. There's a very specific reason for this one. This graph sort of tells us that the likelihood of something being very close to the mean or to the normal or to the average is very high, right?
Exactly.
It- so it's more easier to find things which are average, which are simply normal, which are simply close to the mean of something, right? And the more farther away you get away from the average to the mean, the more unlikely it becomes to find those things. So it's so people sort of represent IQ levels, very intelligent people and retarded people, or sort of mentally challenged people in this kind of graphs. And they say that it's that if the average IQ of a civilization of a human population is 100, right, it's very unlikely or highly unlikely to find people which have very high IQs, like 150, or very low IQs, which effectively means that you are mentally challenged or disabled. It's very unlikely to find those things, those kind of people. And most of the people sort of tend to lie near to the average IQ ranges, which is like around 95 to 90 to around 110, on the left to the right hand side, right? And you can measure this ranges, these gaps, by means of the standard deviation, right? And there's a neat trick to this, right? So if your value, or if your likelihood sort of falls between minus 1 times the standard deviation to positive 1 times the standard deviation, so if your number falls between that, so you can say that there is a probability of 68.2% of the value appearing in your continuous set. If it falls between minus 2 sigma or standard deviation to plus 2 sigma or standard deviation, so there is a probability of 95.4% uh, the probability of it happening. And if it's right around the edges and between minus 3 sigma or 3 standard deviations to positive 3 standard deviations, so the likelihood, or the probability of that event happening, or the value that you will find being in that range, is 99.7% probability. And those numbers make sense, right? These are what you'd call empirical numbers. These are empirical approximate numbers which we have found after studying many normal distributions in real life. And you can sort of almost take a guess, right? So if someone draws you a normal distribution right on the go, you can, by approximating the position where the point is on the graph, or any like away from the mean, you can get a sense on how many standard deviations away they are from the mean. And from that value, you can almost guess and take a hint at how likely or unlikely, or how probable or improbable a value is supposed to be, right? This is extremely useful when we're talking about the probability or the performance of a model, of a machine learning model. We're talking about trying to approximate the distribution of the data, of the training data, of the test data, of the validation data. So we are going to be looking into the practical aspects of using this distribution in real life very soon in our machine learning YouTube series.
And due to this shape of the curve, it's also called bell curve. And also, since Debayan talked about sigmas, this is also called the Six Sigma curve. Since minus 3 sigma to plus 3 sigma, if we add those 3 sigmas, then it will come to be 3 plus 3, that's 6 sigma. This is also called Six Sigma curve or bell curve. So that's an additional information which I thought you would like to know. So guys, let's talk about another distribution which we call the binomial distribution. So what is a binomial distribution? So binomial distribution can be thought of as simply the probability of success or failure of an outcome in an experiment or in a survey that you are conducting, or which is repeated a multiple number of times. So if you repeat an experiment multiple number of times, what is the rate of success or what is the rate of failure? So say for example, I'm tossing a coin for 100 times. So how many times will I get head? So what is the probability or what is the likelihood of getting a head in those 100 times of tossing the coin? That's a binomial distribution. So that's very simply to be put. So here you can see I'll be posting I'll be giving a image of the binomial distribution. So binomial distribution is a type of distribution that has two possible outcomes. That's why the term by, the prefix by comes. By means two. For example, a coin toss has only possible two outcomes, which I just said, a head or a tail. So if I repeat it for 100 times, so we can see. So that's the thing. Like, let me give you another example. Let's suppose you wanted to know the probability of getting a 1 on a die roll. If you were to roll a die 20 times, the probability of rolling a 1 on any throw is 1 by 6. So roll 20 times and you have the binomial distribution of success and that of failure. So that you can easily calculate. It's nothing but a binomial expansion. If you do the binomial expansion, you will be getting the coefficient, you are done, and you can do the same for the graph. So let's now talk about another standard distribution which is very important. We call it the Bernoulli's distribution. So a Bernoulli distribution is a discrete probability distribution. Mind you, discrete probability distribution. For a Bernoulli trial, what is a Bernoulli trial? A Bernoulli trial is nothing but a random experiment that has only two outcomes. That is usually a success and a failure. So I just talked about success and failure in binomial distribution, then I am talking about the same in Bernoulli's distribution. So why? So guys, you may ask that question. So if we perform the binomial distribution for a special case effectively for n equal to 1 for a single case, then we call it the Bernoulli's distribution, nothing more. So if we generalize it for a very large number of times, then we go for binomial. And if we do it for small number of times, say for example n is equals to 1 or 1 time, then we say it's called Bernoulli's distribution.
So the last type of distribution that we're gonna be discussing about is called the Poisson distribution. And please forgive me if I butcher the pronunciation, but this type of this distribution is unique in the sense that it talks about the probability of an event happening which is spread out across time, right? So if you have like machine learning cases, if you have data science problem statements where you're talking about understanding events happening which are spread out across time, as in time across maybe a 24-hour clock, or maybe a week, month, year. If you're talking about data, time series data, if you're talking about things that repeat regularly, and you want to find out what is the probability it's going to happen the next time, when it's happened, at 9 a.m. in the morning, or last week, or like you're trying to predict given time, right? You use Poisson distribution, and this is extremely useful because it sort of encapsulates the idea about probability which is distributed across a time domain. So it's a time domain, time series kind of inclusion into the probability distribution of concepts.
So exactly, like so we understood about five, if I'm not wrong, five distributions, Debayan?
Yeah, 5 core
The
distributions
most important, which we always use.
which we always use in some capacity in our data science, machine learning, or even quantum
Quantum
computing kind of
experiments. Yeah.
journey in our works, in our projects, in our experimentations, in our daily working in our projects every time.
Exactly. So guys, that will be all for the video today. So thank you guys for staying with us for so long. Today we learned about a lot of things, and the main things which we need to learn about probability. We do not need to learn the whole things which are spread across the internet like probability. If you search on internet, you'll be finding thousands and thousands of pages, but we do not need to learn all of those. You just learn this core points, and that will be helpful for your machine learning and data science journey and quantum journey. That's all. So that was also from the industry expert, as you heard. So guys, if you face any problem during the journey, as you know, we have a Discord server already linked down below. So go join over there. I and Debayan will always be over there to help you out with everything and all the questions you throw at us. Guys, to stay updated with all the video series which we post and all the videos which we post, uh, do subscribe to my channel, hit the bell notification icon beside it so that you get notified each and every time we post a new video. And guys, these videos are a lot of effort which we put in, so show some support, and some support from your part would be very much appreciable. and that's all what we asked for. So, without further ado, I was your host Shubro, and with me was
Debayan.
signing off. Bye bye.